We mentioned before that once an optimum value is found in the safe region or the optimum region, we can use the middle value. But there is a better method which is called the simplex optimization. And using this method, you can basically make this process more systematic. And sometimes this method can be used independently, but it will work much better if we use it as a tool to optimize and reach the absolute optimum. So in this part, we will learn about this methodology. The simplex optimization method is also called a model independent method. As the name implies, you're not gonna use um, any model, because before or with the uh, factorial design and the linear regression we're doing it experiments. The factorial design is the experiment side that doesn't change. What changes is the use or the prediction of the optimum value. So before we use the linear regression, for example, to find the optimum value, and then we decide contour plots. In the model independent method, we use a triangle that kind of walks across the response surface. So this is what you can see here is a cream formulation. So you see the surfactant on the x-axis, on the oil amount on the y-axis. So always you move away from the worst result. So the way this works, you test one formulation at a time, and you keep going until you find the optimum. You always move from the worst. And here, as you can see in the triangle, you have you have 3 points. So you see, if you look at the numbers 45, 59, and then this moves, and then you see that you're changing this always, and you draw this triangle until you find the absolute optimum. So you keep drawing this, you measure the values, and you optimize further and further. It has, of course, a different name. If you ever come across it, it's the Nedler-Mead method. Um, and the name is basically is referred to the triangle when we have two variables. Herein we show some comparison of the different methods, the two different where we use a factorial design, and in this case, factorial design, it's a model dependent method. And as you can see, we were able to see before, we plan all experiments up front. We test 9 formulation when we have 3 to the power of 2 design, analyze everything at the end, and we get a regression equation, and we get more data about the system, and that allows us to understand the interactions between the variables. With the simplex method, there is no model. You just plan as you go, so it's sequential. You measure 3 formulations, you start with the 3, you analyze, and you move away from the worst. You don't need to do any equations, less data but faster. And then I would suggest you always do the factorial design, or the if you do a regression equation, you reach the optimum, and within this safe zone or the optimum region, then ideally we should do the simplex method. So maybe this is an easier way to imagine what's going on here. On the left, you get the factorial design, and you're trying to cover the whole uh, space, experimental space. And on the right side, you will see that the simplex, you have 3 points, and you measure and you see. So measure and see, and then you will potentially can end up with lower points to measure. But again, as we mentioned, ideally this method will probably work better after you do the factorial design. So a hybrid approach will probably be the best. Okay, this explains how simplex works. You pick up three starting formulations basically to make up a triangle, and you make them and you test all three. Um, and then out of the three, you find the worst one. And then what you do then next is to flip the triangle away from it. So you make you basically you get away from the worst result. And then you test a new point because you have two good points relatively, and you have a new one which is getting away from the worst, and you test the new point. You do the same process again, and you measure the new point and so on until you end up with the best. So the bottom line you always move from the worst part. This shows you what is exactly going on here. So find the worst vertex of your triangle. Okay, so here if you look on the red is you got 2 3 points, get the best on the green, and you get the worst one is the red. So you look at the midpoint line between the other 2 points, and then you measure the distance from the worst to that midpoint, and then you expand on that direction as you can see here, and then that's the new point is shown in the graph here, is assigned with a star, and that basically the new triangle, and that gives you a new triangle which got these 2 points here, the green and the previous point, and that is highlighted with a star here just to show you the new triangle. The next step in this is the expansion. So imagine that if R, the new point that you measured, if you just follow up from the previous example, we went away from the coarse point. You've reflected, and then you've measured the new point, and it's also good. Then you end up with expanding this, so you're going into the same direction. So basically you're going further in your journey. Let's say for example is the y is worse, so sorry, the r, the new point r is worse, then you do the opposite, you contract, so you do a contraction, and then basically you pull him back. And this way you're gonna find the halfway point between them, and this is on the right graph as you can see here. This is the midpoint between R and M, and you form a new triangle. This is when you do a contraction. This is to help you find the new point, and also to find potentially a new optimum region. So you keep doing this. You expand or contract. It depends. So you might start with the three, and you move away always from the worst. You find new points. You measure them, and then until you find the optimum value. Now the question is, when do you stop with doing all these measurements? The difference from the factorial design method we shown before is that there is no fixed endpoint. So you decide when to stop. And this is often, there are some criteria. Often when the triangle becomes too small, and then that means the difference will not be significant. Or the other possibility is that you change and then results are marginally different, or there is not much improvement. Or you also you basically you reach your target value. So if you reach some value in mind, then this is where it is. And finally, you could also be hitting the boundary limits. We said we always have some boundary limits. We have to know what is the response limits, what is the acceptable value, and we said we check this in some credible sources. And you need to be aware that uh, there is something called local minimum. All right, the local minimum doesn't mean it's the same as the global, the absolutely best value. So you need to be careful here. So you've got to in fact, this is probably one of the disadvantages of simplex, because you might end up with a local optimum. Doesn't mean it's the best, but in some region is giving you some kind of better value, but it's not really the absolute optimum. Now, these are some of the advantages of simplex. You probably can imagine or you predict some of them. You can see that there are fewer experiments to do, and you may reach an optimum faster. Um, but then we will see that this is probably better for fine tuning. And it works without even knowing the system. So you can just do experiments without even going to, do all this kind of factorial and all these set limits. Um, Now, we often use graph paper, and that's for obvious reason here, because you can have the coordinates and you choose your value. So using graph paper is the right way to do it. And the good thing about it, it adapts as you learn, because you understand what is going on with your system. And it can also handle boundaries and limits, because you can always contract if you reach some kind of region, they can contract without going beyond your boundary. Now, these are often the ways or the kind of criteria we use when we want to use either of those two methods. So in many cases, when factorial design is needed, when you really want to understand the system and there is a potential for interactions. And then often we want to model the findings to find a prediction equation. And of course, this is going to be more, it requires more time, and if we have the time, that will be the right way to do it. We start from scratch, and we need to have a kind of justification or explanation to others, a way to communicate the data. And it's really important to have a good quality of data, because we're going to use those for the prediction and data fitting. For the simplex, we just need to know, if we are interested in just the optimum, then it might be okay. If you have limited time, it's often quicker, and in many cases you're going to fine tune an existing formula. And then you would probably have some understanding of the system, and you might well use it to do fast, quick screening of the system. And in many cases, the response surface is simple and boundaries are well defined. These are kind of criteria that you would use the simplex. In reality, the best practice is use both methods. So I suggest you start with the factorial design. You cover the whole space, you understand the system, and roughly you will know where the optimum is. And then that will also allow us to understand interactions. After you know your optimum region, then you can fine tune the region to find the absolute optimum. And you use simplex to fine tune the data or the parameters. So you start near the factorial optimum, and you end up with hopefully the exact best formula, and that will allow you to confirm the final formulation.